So in preparation for my next project, I need to make a tool to help me out. And I have a steady rest on my lathe, but it only goes to about 6 inches diameter, and I need to turn something 7 inches diameter. So my solution is to build a larger steady rest. Hope you can see that. Had some 2-inch steel cut out, plasma cut it, and it turns out I probably should have had it water jet cut, but in any case, here it is. And so for the next few episodes, I'm going to be working on turning this into my next steady rest that will handle up to 9-inch diameter materials. All right, let's get going. Oh, before I go, a couple design considerations I've changed. You'll notice that these sides are both flat. Typically, steady rests are designed like this one, with one side being pinned and the other side being removable, so you can flip up the top, insert something, drop it back down, and lock it. I opted to do something different for a couple reasons. One, the pin does add a little bit of slop to it, not a lot, and that wouldn't be catastrophic. But the second reason is because these pieces each weigh about 30 pounds. So if this was one assembly, by the time I'm done, this would weigh close to 50, so, or more, actually 60. So I'm opting to make the top piece bolt on in 2 spots, and I might pin it as well. I haven't decided yet. We'll see how it is. I think it would make a better mating surface anyways, and be more solid. But I'm not sure how rigid the top part needs to be anyways, since most of the weight's supported on the bottom. So I'm really not quite sure, but this is how I'm going to proceed. So I'll see you in a while. So the first thing I'm going to do is I'm going to take this piece of spare stainless, and I'm going to make a thread gauge out of it, so that when I make the threaded screw parts that insert into the steady rest, I'll be able to make sure the threads are correct to know when to stop. So that's what I'm going to start with first. I won't bore you with all the hole drilling part. So because the threads I'm going to cut on the steady rest itself are going to be using this tap, I'm going to cut the thread gauge with the tap. The parts that rotate in are going to be cut using traditional thread cutting methods on the lathe. So this is going to be my reference, because this is what's making the cut. If you're wondering where they go, each one of these points is going to be drilled, bored, and tapped. Drilled and bored 1 inch all the way through, 1 3/8 tapped to about here. All right, so here's the completed thread gauge, and I followed a chart that says that for aluminum, brass, and plastic, 75% thread, stainless steel, iron, and other steels, 50% threads. But I got to tell you, I think these threads are kind of shallow for my taste. They're really flat on top. So I'll probably try and do 75% thread and see if I can get the tap through it. It's a long way. I want to tap like 1 inch and change, or maybe 2 inches. That's a long run, so we'll see if we can pull that off. If not, I can always bore it out a little bigger. So to start this project, one of the things I need to do is I need to face this material just to give myself some flat surfaces to work with, since there aren't any reference surfaces anywhere on this. But I wanted to test my tooling before I work on the expensive pieces that I had cut. So I'm starting with some cold rolled steel, and this stuff needs to be, this piece here is for the clamp that goes underneath. This is the clamping piece, and I need to dimension the stock. So what I'm working on right now is I'm testing out this this roughing finishing combination end mill, just to see how the finish is. And you can see just one pass here, it's actually really nice. It cuts like butter and produces dangerous little needle chips, and but it works really well. It takes off material really quickly. So if I go this way, it's climb milling, and it basically just pulls it right through. It's terrible finish, but it just removes material like there's no tomorrow with almost no effort. When you do conventional milling, going the other direction, you get this great finish, and it's a little bit of force, but not much. And anyways, I'll bring you right back. Well, here, let's see a pass. So of course, conventional climb milling, it's trying to pull itself through. But not a problem. It's not like it's going to be a runaway or anything. It's just making almost no force going through. The finish, well, is what you expect because it's not going evenly into the cutter. So going back the other way, we're going to do conventional. So you can see the finish is excellent. Takes off material like there's nobody's business, not even struggling. I'm going 600 RPM here. When I do some face mill tests on this stuff. So the next part of this test is I'm just going to face this piece, not that I need to. It's just I want to check out how this face mill works. It is a round insert, an RTMT or something like that. Inserts a round insert, which are the strongest inserts, but I'm not quite sure how the finish is going to end up. So I'm going to take a light pass over this surface. And I could have gone for a larger diameter, but a larger diameter would take more torque because you got a bigger torque arm as the cutters are sitting out here. Plus more cutters will engage at any one time. So I'm trying to minimize the stress on the mill. But I think the mill probably could handle larger because my other face mill, this one works fine and it is much larger. So anyways, I thought I'd start with this one because it's sort of a test anyways. And I haven't done as much steel, which is what this is. This is cold rolled, so I'll bring you back. All right, so I'm going to do a 10,000ths pass, a really light pass, and just see how it goes. Moderate feed rate. It's actually pretty fast. I think I need to check how tight I made the cutter on the arbor, only because it seems like it's wobbling a little bit. It sounds kind of like it. And look at the finish here. The finish looks like there's a couple thousandths wobble or a thousandth wobble there. So let's see what we can do about that. Here's the 10,000ths cut. Nothing was particularly loose. It definitely prefers cutting in one direction over the other, which I believe is climb milling direction. It's much better finish. The finish is still smooth to the touch, but not anywhere near as nice as you'd hope. This is a cheap Taiwanese cutter though, so $30 versus say $500-600 for a Sandvik. That might be the difference right there, but you can't really feel too much difference. So one thing I did do was I tried several RPMs going up. I started at 500 initially, and the chips were coming off metal colored. Then I went to about 700 and they came off straw. So then I bumped it up to 1200 RPM. And they're coming off blue, but the finish improved noticeably. One other thing to note is that because these are round inserts, they're only cutting at the peak of the insert. So if you're trying to eyeball and go from edge to edge, you know, the outer edge is actually not going to cut. It's going to be in half the insert diameter roughly. So just keep that in mind when you're trying to do, you're trying to overlap paths. Anyways, there's the finish, if you can see it. There is scoring on it, but you can't really feel any of it, even with your nail. Well, a little tiny bit with your nail. Not bad. Not overwhelmingly beautiful either. But then what do you expect for the price? All right, I'll bring you back. I think as long as I got this piece in here, I'm going to drill and tap it for 3/4 and call this piece done. Here's a close-up of the cutter. I made sure all the inserts were tight, the clamps were tight. Just to show you the fit and finish, these keyways, definitely not even close to precision ground, kind of sloppy. So all of your force to tighten it is on this 1 Allen, which I did reef on a bit. Yeah, I mean, in some regards you get what you pay for, and so I can't expect the glass finish out of this. If round inserts can even yield one, I'm actually not sure, having never used one. So a lot of unknowns, but it's acceptable. It's not great. I think another thing I did do that might improve everything would be to lock off every axis that's not moving. So the Y and the Z axes, I could have locked those off, which I did not. So maybe there's enough torque that you're getting a little bit of motion there too. I will give it another shot when I come back to this part to use it on the main pieces over here. And again, we're not looking for precision finish anywhere. So the only thing that needs to be somewhat accurate is the holes drilled and tapped down the center, and not because alignment to the center position is ultra critical. It's mostly because there's not a lot of extra material with the size holes I'm drilling. So you just don't want to waste any of your material just to keep the strength up. The diameter of the part that is supporting on the center, I cut a hole that's 1 inch diameter down here and 1 3/8 tapped up here. So the meat of it is supported by the main body. This is just for radial force out from the center, but it's in line with the threads, so it should be okay. It doesn't need a ton of strength there. I think the rotational force is going to be handled by the main meat of this, because the shaft is 1 inch, and I'll do a fairly close bore so it's really tight in there so that it can't move too much. Other than that, there really aren't any precision alignment parts on this. So we're just going to proceed. Next, I got to get the vise off the mill, which is always fun, being as heavy it is with a bad back. I still got to finish that one piece. I'm just going to drill and tap it. I won't show you that. And then I'm going to come back. I'm going to face this. Then we're going to start facing all the reference points, which are the mating surfaces here. Well, I'm going to start with both sides flat, so I have something to clamp to, and then I've got to do the mating surface here, and I'm going to get these square on the ends so that I can use to find center between these two. These guys, I need it flat here, but I might come on the sides and square it off just down a little bit so that I have something to measure off to find my center. I will flatten these bottom faces because they do ride on the mill, and that I will try and get very square if I can. This part, again, doesn't matter. It protrudes down, just got a hole. Don't even need to finish it at all. This groove's going to be a bit of a challenge. I still haven't mentally worked out all of the kinks and how I'm going to pull this off, because that aligns with this ground surface right here. So I probably want to get that to fit reasonably well. So let's move along, and I'll be back in a bit. So the last step of this process of making this part is tapping 3/4 tin. And I did 70% threads, even though my table said for harder metals you should do 50%. But if you look at 50% threads, they are not very deep. So I tried to do 70%. And actually, based on the drill bit I had, it's 2/1000 over 70%, 75%. It was really pretty difficult. My concern is when I get to the 1 3/8 threads, I am not quite sure how I'm going to pull that off. I mean, I might just have to get them started here in the mill and then work them over to the vise, where I have purchased a Greenfield large tap handle, but I don't know. This is going to be really challenging to get them down like an inch or two. So we'll just play it by ear, but my initial test more or less successful. I'm a little concerned how I'm going to pull off the tapping. I'd rather do it in the lathe, except I can't turn the whole piece in the lathe very easily. So we'll do what we can. So here's the final lock-in piece. It will be mounted in here, recessed, countersunk. Probably I'm gonna have to use a boring bar for all that, but anyways, this grabs up on the lathe bed from the bottom, and this goes in the top. So let's move on to this guy and face it. Alright, so I've got some heavy clamps clamped down tight. I'm going to be taking very light passes, 10,000ths at most. So we're going to start here and come straight forward and see how that works. I want to see if this moves at all, because I don't have a lot of experience clamping to the table. It might need a couple more clamps. I guess it never hurts to have extra, but definitely hurts to have too few. So I might add a couple more. Anyways, I'll bring you back. Alright, so I'm testing out. This is a 10,000th depth of cut here on the Z 10.8, and I've already gone in a little ways. We're just going to go back and go very slowly. 1200 RPM. I'm getting blue chips, as you'll see. Seems to be able to handle a 3-inch wide bite pretty well. Didn't quite clean up everything, but that's okay. Alright, so I'm going to make a couple more passes and clean up some other areas, and I'll bring you back. Alright, so it performed pretty well, even a 3-inch cutter on this mill. I think it might be as large as I want to go. I don't really know. It seemed to handle it okay. I've locked everything down but the X and Y axes, so the Z axis and the quill. The finish is pretty nice, and it's flat for the most part. I got a little lift right here, tiny bit. Gotta check out what's going on there. In any case, I think we're good, so I've got to deburr the outside edge, flip it over, rinse and repeat. Okay, so can you tell which one I've done? Right, one down, one to go. So 2 sides of this one to do. Then we just have squaring some other sides off just for reference surfaces. All right, okay, so here we have more or less level. And next time we'll be squaring off some sides and flattening the tops and the bottom. This guy, these surfaces in here. All these are going to require some interesting clamping processes, which I haven't even figured out yet. So I will see you next time. Hope you enjoyed it. Hope to see you on part 2.